Before we get to discussing the architecture of the GPU, here is a very brief and simplified history of GPU computing. Some of you may remember that at the beginning there was no separate graphics processing unit, and instead of graphics cards, the graphics were actually rendered by the CPU and sent out to the display directly from the motherboard. However, the rise in demand for high-performance rendering in games has led to the production of separate graphics cards, i.e. cards having separate graphics processors, which actually took care of the rendering of an image and its display on a connected monitor. And the final kick, if you will, that made the GPU revolution possible was the introduction of the possibility to program GPUs using small programs called shaders. So what's a shader? Well, a shader is a small program that can run on a GPU in a highly parallel setting. And this program is transferred to the GPU and then executed in parallel on many threads. And there are actually two types of shaders. There are vertex shaders, which determine the position of a vertex. And this allows programmers to basically redefine the coordinates of a particular point in space. So you can take a model and deform it, for example. And the other type of shader, perhaps more interesting to us, is the pixel shader. And this shader lets the programmer determine the color components of an individual pixel. And this in turn allows various interesting image effects to be applied. Now, these shaders can be programmed using languages such as HLSL if you're using Microsoft DirectX, the high-level shader language, or GLSL if you're using OpenGL, and this is the OpenGL shading language. And both of these languages are roughly C-like in appearance, but the main problem is that they're both intended for graphics, and as such they're not so suitable for general purpose computation. However, back in the day, that's all that people had. So for example, to perform matrix operations, you had to basically convert your data, so convert your matrix into a texture, then run the pixel shader on the texture, and then convert the resulting texture back to data. And it was doable, but it wasn't very easy to do. So the whole idea of doing computation on GPUs, it actually gave birth to a new field of computation called GPGPU, which is short for General Purpose Computation on GPUs. But why did graphics cards become so popular for general purpose computation? Well, it was all to do with their highly parallel nature, and graphics cards were designed with parallel processing in mind. The idea being that you could process lots of vertices or pixels or whatever at once in parallel using a very large number of threads. And this implies that the GPU has a much higher throughput than the CPU. So even if the CPU is faster, it can only do so much in parallel because, typically the CPU is constrained by the number of hardware threads it can spin off, obviously taking into account the number of cores as well as hyperthreading. Plus, of course, there are many ways of speeding things up by using SIM, those special CPU instructions that work on memory registers of larger sizes, say 128 or even 256 bits, and perform operations on multiple sets of data. But the GPU simply has a lot more concurrent operations that it can perform at once. So even if the GPU clock cycle isn't as fast as the CPU, it still gets a lot more done. Another factor in the success of GPUs has been the fact that graphics cards are essentially off-the-shelf products. Every gamer out there needs a good graphics card, and this has allowed GPU manufacturers to recover their R&D costs and keep the prices relatively low compared to custom-built acceleration solutions. And finally, graphics card manufacturers realized what was going on, and they started offering ways of programming the GPU that weren't tied to graphics anymore. And this has, in many ways, untied the hands of all those developers who perhaps didn't want to delve into DirectX or OpenGL just to get some number crunching done. So today we have things like the NVIDIA Tesla platform, which is a GPU that doesn't even have display output ports because it is dedicated entirely to computation.